In this muscle physiology course, we will focus quite a bit of attention on contractile mechanics. A cornerstone of contractile mechanics is the force-velocity curve, and today we'll discuss the concentric side of the force-velocity curve and the mechanisms responsible for its shape. Concentric force-velocity relationship is characterized by an isometric maximum force at zero velocity or isometric, a maximum shortening velocity, here represented as 1 because it's velocity over v0 or maximum velocity, so this is maximum velocity here. And in between is a hyperbolic relationship where force decreases more rapidly initially with increasing velocity. This relationship was described early on by A.V. Hill, and here's one formulation of his equation. This is the way I code it in my models. So it's your isometric force term here, multiplied by 1 minus the relative velocity, v over v0 is relative velocity, and then all of that divided by 1 plus relative velocity divided by this A coefficient divided by the isometric force. So isometric force, velocity, max velocity. A is what Hill called the coefficient of shortening heat. And it's thought to represent some sort of loss of force to heat. We very often write this A over F0 term as AF, and it actually represents the curvature of this relationship. So while this equation does a nice job of describing force-velocity relationship, it doesn't do much to explain the mechanistic basis. And so that's what we'll do here directly, is talk about what mechanisms might be responsible for the shape that we see in shortening muscle. So concentric means towards the center, so it's a shortening contraction. And during the cross-bridge cycle, myosin heads, as you've seen in some of the animations, can either be attached to or detached from actin binding sites. And so here you see an animation where you have a set of myosin heads here bound to actin filaments. And as they go through their power cycle or power stroke, you'll see them move the actin filament, then reset and find another binding site later on. So in the simplest of terms, you can think of the myosin head either being bound to an actin or not. Two states, attached or not attached. And it turns out that it takes a relatively constant amount of time for a myosin head to find and attach to an actin binding site. And so that represents the time spent in the detached state, and we're just going to call that T sub D for time detached. The power stroke of the cross-bridge cycle, however, is a relatively fixed distance, not time. So the time spent attached decreases with velocity. That is, the time attached is proportional to 1 over the velocity. If this is a little bit hard to grasp, imagine that each one of these cross bridges goes through a cycle that's 1 millimeter, for instance. It's much, much smaller than that, but let's just go with it. And if the muscle is contracting slowly, that means it takes a long time for it to go through that 1 millimeter distance. If it's contracting very fast, then that 1 millimeter goes by very quickly and doesn't take much time, so the time is reduced with increasing velocity. So these two times, the detached time, which is constant, and the attached time, which is proportional to 1 over the velocity, can be combined to form an expression for the portion of total time during which cross bridge is attached. So we'll go time attached divided by total time. So that's T sub A, we'll call it here, divided by the attachment plus the detachment time. And as we derived up here earlier, attachment time is 1 over V, and we're going to divide that by the sum of these two, so 1 over V plus the detachment time. Now, it's common in muscle physiology and muscle mechanics to express velocity relative to maximum velocity. So V over V0 is relative velocity. And so then this equation becomes this one, 1 over V0, divided by that same term, 1 over V over V0, excuse me, plus the detachment time. And it turns out that if you graph that equation and you select an appropriate value for detachment time, you get a hyperbolic curve that looks very, very much like the Hill force-velocity equation. So this is the curve that simply represents the proportion of total cross bridges attached. And of course, cross bridges only produce force when they are attached. So this should represent a big portion of the overall force-velocity curve. And you see that it looks similar and in fact decreases quite a bit with increasing velocity. So is that mathematical sleight of hand, or is it actually meaningful? Well, in this paper on the shape of the force-velocity relationship in skeletal muscles, the authors report that the number of attached cross bridges, shown here in the solid line, decreases, essentially hyperbolically, with increasing muscle shortening velocity. So it looks very much like the curve that we just derived with a couple of assumptions about attachment and detachment time. These authors also reported that force generated from each cross bridge decreased with increasing shortening velocity, at least after some threshold was reached. So not quite sure what's going on over here, but then at some point force decreases. But another group has reported the force per bound cross bridge with a little different shape. A nice linear portion down here, and then actually a rapid increase as you get closer to zero. So, who's right? I don't know. I don't know whether this is appropriate or that is. But generally speaking, they both have a linear decrease over a large portion of the shortening velocity. One possible way to approximate that decrease is with a linear relationship, which is isometric force multiplied by 1 minus the relative velocity. So this would decrease to 0 at Vmax, which is what we know force does. And so if we put that together with the portion of attached cross bridges, which we derived a minute ago, then we would get this equation. So the force per cross bridge multiplied by the portion of attached cross bridges. And when you do that, again, if you select an appropriate value for the detachment time, which can be related to the Hill coefficients here, then you actually get exactly the Hill equation. So here's my model, the combined model, and here's the Hill. And you can't actually see the black because the red is on top of it. And so if you pick a value for detachment time that's 1 over the AF term, or is isometric force over the hill A coefficient, and you substitute that in here with a little bit of algebra that I won't bore you with, these two equations become identical. They are exactly the same equations approached from two completely different thought processes, and this is a little work that I'm doing right now and should be submitting sometime soon. So to wrap up, the portion of attached cross bridges decreases with increasing velocity, and that's equal to the time for attachment, which is a function of velocity, divided by the total time, and then cross bridge force decreases with velocity, which is a function of 1 minus the relative velocity. And so I hope that that helps to shed some light on why the force decreases in the way that it does during fully excited muscle shortening. Thanks very much, and I will see you Tuesday.